Now let's come back to this example. You have two icebergs with some frictionless link, one with mass m, boat 1, and one with mass 2m, boat 2. When exert the same force on both, and they travel same amount of time. Which one has more kinetic energy? Which one has more momentum? Pause this video, think for about 1 to 2 minutes until you figure it out. Okay, now welcome back. The answer should be they should have the same amount of momentum this time. And why is that? Because you have same force and the same amount of time. So you have momentum equals F times delta t. And F are the same, delta t are the same, change of momentum should be the same for both boats. Okay, so if momentum are the same, which means boat 1, this one should have velocity v, and this one should have velocity 1/2 v, because they should have the same momentum. And then you need to calculate which one has higher kinetic energy. This is for boat 1. This is for boat 2. So apparently boat 1 would have more kinetic energy. And just using this kinematic equation, Vf subtract Vi equals A delta t, and if you just do an integration, you will find out and we call this one impulse momentum theorem. So change of momentum should equals to an integration of force over time. Now, integration of force over time, we call it impulse. Now, if you don't like integration, let's just make it simpler. If f is constant, then this integration simply gives you impulse is f times delta t. Impulse is just f times delta t if f is a constant. Now, of course, if f is not a constant, you could do an integration of f over time. Now, we have to do a note of integration of f over time. For example, if you have velocity versus time plot, then an integration of velocity over time would give you displacement, right? Now, if you have acceleration over time, the integration of acceleration over time give you change of velocity. Now that's the same thing. So if you have f over time plot, then you have the area and this plot will give you impulse. Now a lot of case, the force is not a constant. So we want to find out how big is this impulse, or what would be the average force induced by impulse. So we introduce a concept called average force. So as long as this average force is the area under this rectangle equals to the original impulse, we call this is average force for the impulse. And this is something we can utilize in our everyday life. For example, somebody threw an egg to you. So you can just ask a family member to try. You can try this. So one threw an egg to you, you try to catch the egg. By your instinction, your hand is not going to be stopped at the place of impact. By instinct, you're going to move your hand from here to here. It's just like when you're playing basketball. If you play basketball, you know somebody pass you a ball, you're not going to catch the ball and your hand stays there. you're going to move your hand along with the direction of movement of the basketball. And why do we need to do that? Because we want to reduce the average force exerted on our hand and on the egg. Now, if you keep your hand there, there is a good possibility that the egg is going to be broken because the average force is going to be large. Okay, this is an example we want to find out what's the net impulse for this force. So you just need to find the area under this curve. Now this big triangle will give us positive impulse, which is 1/2 times 2000 times 8 subtract 2, which is 6 millisecond. So times 6 times 10 to the negative 3 equals, let's see, 6. This is 6 Newton second. And then you need to calculate the area of these two triangles. Now this one is 1/2 to 500 times 10 to the 3, which is 0.5 watts. So this is 0.5, this is 0.5. So the net contribution of these two are -1 because they are negative. So you have the net contribution impulse net is 5 Newton times second. Another example, so you have a ball, 0.4 kilogram ball moving at 30 meters per second to the left at the beginning, then rebound on the wall, and after the rebound, its velocity is 20 meters per second. What's the impulse during the collision? And if it's in contact for 0.01 second, what's the average force acting on the wall?